Let's now have a look at series. Here we're going to look at some of the groundwork for working with series. It's assumed that people have met before arithmetic and geometric series. We'll also take a look at the concept of convergence. In this course, we'll use a working definition of a series, a set of terms added together. We have some examples of series here. We can see each of them seems to have its various differences here. Now we see, for example, series A and D. Those contain only a finite number of terms, 5 in each case, while series B, C and E each contain an infinite number of terms. The notation here with the dots means continue indefinitely, continue for an infinite number of terms. Series D and E, they contain various powers of x. Those are known as power series. Now, one very important property of an infinite series is convergence. It might be that as you take more and more terms in a series, the sum settles down to a constant value. And if that happens, the series is said to be convergent. On the other hand, it might be, as you take more and more terms, the sum increases without limit. If that happens, the series is said to be divergent. Here we have an example of a divergent series. We use the notation here for the series, but we can write out the first few terms here. The sum from the first term to however many terms we want of 1 over I. So we have 1 plus 1 over 2 plus 1 over 3, 1 plus a half plus a third plus a quarter, and so on. It turns out that even though the terms are getting smaller, if we take an infinite number of terms, the sum of the series increases without limit. If we take millions of millions of millions of however many more millions of terms, we can get the sum of this series up to 100, 1,000, and so on. By taking enough terms, and yes, sometimes it will need to be a large number of terms, the sum of the series can increase to any value that you put in. This is a divergent series. On the other hand, let's imagine the series here. It's the sum of 1 over I squared, 1 plus a quarter plus a ninth plus a 16th. It turns out no matter how many terms we take in this series, the sum will not become greater than pi squared over 6, around 1.65. So this one here is a convergent series. Take as many terms as you like, you will not get past this limit here. This series converges to the value mentioned here. Now, if you have an arithmetic series, this is divergent. Either the terms become more and more positive, and it'll diverge off to positive infinity, or the terms will become more and more negative, and it'll diverge off to minus infinity. Geometric series, however, are sometimes convergent and sometimes divergent. They are convergent if the common ratio lies between -1 and 1. If each term is smaller, as in closer to 0, than the term before, then a geometric series will converge. And it'll converge to this number, a over 1 minus r. However, if your common ratio is greater than or equal to 1, or less than or equal to -1, it's a divergent series. Well, let's see an example here. Here we have a geometric series, 25 plus 5 plus 1 plus a fifth plus a 25th, and so on. We're asked here for the sum of 4 terms, 5 terms, and in fact the sum of all terms, the sum So here's our geometric series. We see the first term, a, that's equal to 25. The common ratio, each term is 1/5 of the term before. And now we're in a position to find the sum of the first n terms. So we're to call it Sn, the sum of the first n terms, a well-known formula for the sum of the first n terms, a times 1 minus r to the n over 1 minus r. And in terms of the numbers here, we have 25 times 1 minus 1/5 to the power n over 1 minus 1/5. So we deal firstly sum of the first 4 terms. Put n equals 4 into here. So S4 will be 25 times 1 minus 1/5 to the power 4 divided by 1 minus 1/5. Or what we'll have here, 25 times 1 minus 1 over 625. So that would give us 624 over 625, all divided by 4/5. And when we work this one out, 31.2. Now, the sum of the first 5 terms. S5, working from here, 25 times 1 minus 1/5 to the power 5 over 1 minus 1/5. Work it out in a similar manner, 31.24. But then the sum of an infinite number of terms, if we were to continue, 1 over 125, 1 over 625, and so on, the sum of all terms, or indeed the sum to infinity as we call it, S infinity is a over 1 minus r. And if we did start from here, if r lies between minus 1 and 1, we let n tend to infinity, we do see that this top line will tend to 1. In this case, we will get 25 over 1 minus 1/5, which would be 4/5. We'd get 125 over 4, which of course in decimals comes to 31.25. Now of course, just considering the first few terms, if we were to just add 25 plus 5, that's 30, 30 plus 1, 31, 31.2, which is of course what we got here. Add on 0.04, we get 31.24. And indeed, if we continued to add on more and more terms, 31.2, 31.24, 31.248, 31.2496, we're gradually getting closer and closer to this limit here, 31.25.